Okay, we're going to do the Wiggers diagram, right? Sort of the culmination summary of the electrical and mechanical actions of the heart. Right? It kind of ties everything together. So we'll start with the ECG at the top. Right, we'll label that, right? So that's ECG. ECG, EKG, same thing. K is the German version. We have P wave, corresponds with atrial depolarization. We have the QRS complex, which we'll see momentarily corresponds with atrial repolarization, but the majority of it is actually ventricular depolarization. And then we have T wave, and then we are back to the P wave over here. Right? Remember that the flat line portions of the ECG are called the isoelectric line. Iso meaning same, electric meaning charge. And what that really refers to is the fact there's no voltage being generated in the heart during those times, right? There's no separation of charge between one region and another. So the waves are going to occur where we have separation of charge and a dipole, meaning, and that occurs when we have areas that are partially depolarized and partially repolarized, or partially repolarized and partially at rest, whatever the scenario of regions that are differently charged at that moment. Right? Don't forget, so, and we'll point to these in a minute. So we've got this piece right here would be the PR segment. We have the ST segment. Right? Maybe I should make these some color here. Add some color. Yellow stands out. PR segment, ST segment, and then the TP segment right here. Okay, and those are going to be important because it's not just during the waves that things are happening, right? In terms of the heart's contractions or relaxations or blood moving, that kind of thing. Okay, so now to show you the derivation of the ECG, where it comes from, we have to show you the action potentials of the individual, well, not of all four chambers, but of the atrial chambers, and as opposed to the ventricular chambers. So we did an atrial cell action potential. Right? So that's atrial action potential. Now remember, to get those action potentials, we'd actually have to have the SA node fire, right? Which we don't have it on here. We could put it on here. Again, that guy would fire about here and about here, right? It has to come before the atrial cells depolarize, because it's the stimulus for the rest of the atrial cells to depolarize. This would be the atrial cardiomyocyte action potential, right? Not the nodal cells. Nodal cells would have to be earlier. And again, you don't get a wave because of their firing, their depolarization, just because it's such a small group of cells doing it. Okay, so let's add the ventricular cell action potentials, ventricular myocyte action potentials. And that would look like this. And then run right off because we don't have our next QRS complex, so I don't want to start the next one there. Okay, so that's ventricular action potentials, right? And remember, for both sets, there's not one cell. Remember, this is an intracellular recording. Both of these are intracellular recordings. This is an extracellular recording. But it's what the individual cells are doing as groups that causes the waves in the ECG, the extracellular recording. So what I did in class, what I'm going to do here, is sort of show multiple cells depolarizing and multiple cells repolarizing, right? They don't all do this at the exact same moment because the action potential is traveling cell to cell. It's like saying, remember the dominoes falling, right? The dominoes do not all fall at the exact same instant. They fall one after another after another. So we have some that are depolarizing early and then a few that are depolarizing later. Same thing with repolarization. That's actually even more spread out. I'll do the same thing up here in the atria, with atrial cells. Right. Okay, so again, those are superimposed action potentials, just some a little bit earlier and some a little bit later. Now, because so we sort of point to a spot, get another one under here, right? Point to a spot somewhere in the middle of this, and again, or the middle down here, where some are and some aren't depolarized. Well, that creates a dipole, which is a voltage, right? And because of that, you get a wave, right? And so that corresponds with the P wave, this, but largely more so this, because again, there are way more cells in the ventricles than in the atria, right? And then our T wave corresponds with ventricular repolarization. Okay? Now, having said that, remember that when we are fully depolarized in the atria, we're in the PR segment. When we're fully depolarized in the ventricles, we're in the ST segment. And when we're fully repolarized in both, we're in the TP segment. Okay? So what we're going to do now is correlate these action potentials with the contractions. Well, the contractions, right, the job of the contractions is to compress the blood, increase its pressure, and drive it into the next space that it's supposed to move into. Right? So for the atria, that next space would be through the AV valve and into the ventricles. And for the ventricles, that next space would be out into either the aorta or the pulmonary trunk, depending on which circuit we're looking at here. Usually the Wiggers is drawn for the left, so of course that would mean that the space we'd be talking about moving blood into would be the aorta. Okay, so but instead of looking at tension, we look at the pressure generated from that tension, and we put that trace up here. Okay, so I'm going to put the atrial contraction and the pressure it generates directly under the plateau. Remember, the plateau is when it's a balanced calcium and potassium flux, calcium coming in, potassium going out. They sort of cancel each other out so that we end up sort of with a level degree of depolarization, kind of stays the same. But because of the calcium influx, which causes intracellular calcium release, which binds to troponin, which moves tropomyosin, which leads to cross-bridge formation. Cross-bridges generate tension. So that's where the tension will rise and the pressure will rise. So my pressure increase will sit somewhat underneath the plateau. So here's my atrial pressure trace. Notice it is not a very big blip in pressure because these are very thin-walled. Remember, like 1/10 as many of these cells as there are of these cells, right? So they can't generate a very strong contraction because there's just not enough of them, right? And then pressure remains low all the way over to our next action potential. I should come leap up there, yes. Okay, so that's atrial pressure. And again, you could call it atrial tension if you prefer. They're going to be very similar, or go hand in hand, I should say. The traces would be very similar. Now, if I put the ventricular pressure trace on here, right, matching it up with the color here, red, of the ventricular action potentials, they're very relaxed during their diastole, and so and remember the venous blood flow is flowing into the atria first, and so it keeps the pressure there a little bit higher. And so the pressure here is going to be lower until we get our action potential, and then we get a big spike in pressure. And then again, when it repolarizes, we lose our pressure, and then we're lower and lower and lower, and then of course, we get the next cycle over here somewhere. Okay, so that's ventricular pressure. Okay, now we do have two spots on here where the lines are crossing, so we'll circle those. I'm going to circle those and then come back to them for a second. But remember, this is where atrial and ventricular pressures are sort of swapping who's higher and who's lower. So we have to talk about what separates the atrium from the ventricles, which is the AV valve. Same deal over here, except the pressure flip is going the opposite direction. right? Now the ventricular pressure is falling below the atrial. Here it's going above the atrial pressure. Okay, we'll come back to those in a second. Let's put on here the blood pressure, the arterial blood pressure, right? And that pressure in that space, right outside of the heart, would be doing this. Right? Falls and falls and falls until the pressure in the ventricle exceeds the pressure in the aorta, right? And opens up the semilunar valve. Put that on here in a second. And now we're pushing blood out into the aorta, so the pressure out there rises because we're squeezing more blood into that space. Then the ventricle starts to relax, so that pressure starts to fall, and eventually, right, the ventricular pressure falls so fast it falls below the arterial pressure. Okay, and of course our semilunar valve is going to close there. Now the aorta, that space is separate from the ventricle again, and the pressure out there is just going to do what it does, which is fall, because the blood is moving off into the circuits, right? As the volume in the aorta and other large arteries sort of moves off into the smaller and smaller vessels, well, the pressure there falls because there's just less volume stretching the walls. Okay, so let's circle our other two intersections here. This one, this one. Right, so here, let's back up. So here, the ventricular pressure exceeded the atrial pressure in blue, so that would mean the ventricle would tend to be pushing blood back up into the atria. We don't want that. The AV valve closes. So this is AV closes. We get a phase where the pressure rises, but nothing is happening. In other words, no volume is moving or leaving the ventricle. We'll label that in a second. Then it does exceed the arterial pressure. Remember, be careful with arterial versus atrial. They sound very similar, but they're not the same. So when that ventricular pressure exceeds arterial pressure, the exit door from the ventricle opens. That's the semilunar valve. So that's semilunar opens. Then we get so as it's opening and the ventricle's contracting, that means we're ejecting until pressure starts to fall and the semilunar closes. Blood tends to sort of flow backwards towards the heart for just a split second and close the semilunar valve. Right? Remember, in between here and here. Move that over just to here. Right? We get ejection. When our semilunar valve is open, we're moving blood out into the arterial circuit. Okay, now one thing we can label on here actually is our peak and trough, low, high and low pressures in the arterial circuit. Well, they're clinically relevant. We measure those every time we go to the doctor's office, right? They put the blood pressure cuff on your arm and pump it up, and again, we learn in lab about how that actually estimates your blood pressure. But what they're estimating is this pressure and this pressure, right? And so those correspond to, and now the terms will hopefully make sense. And so this pressure is your systolic pressure, like your right? Looking at the green line here. It's your maybe I should put that in green, huh? So we can correlate the two. Right, that's your systolic pressure. Right, I'm just drawing a line over to this point at peak pressure. Because it's the pressure in the arteries during systole, the peak pressure, which is going to occur when we're ejecting blood into that circuit, right? So the low pressure right here, and I'll go backwards for this one, is called, of course, the diastolic pressure, right? It's the lowest pressure in the arterial circuit at the very end of diastole, just before we start to pressurize the blood, or just before we start to eject the blood into the arterial circuit, which is when the pressure there will start to rise. So that's diastolic pressure. Right? And remember, this line is arterial So our arterial pressure falls and falls and falls to the diastolic pressure. Then it gets increased as we eject blood to a peak, which is the systolic pressure. And then, of course, it's going to start to fall again towards the diastolic next cycle. Okay, we've got our valves opening and closing. We have all our pressure traces. Now we have to draw the ventricular volume trace. Right, so I have to drop down here. I'll put that one in purple. Actually, green might show up better. Green. Right, and so if we go all the way over here to the left, I'm trying to get myself out of the way here, we've got this a scenario at the very beginning of this particular cycle where the atrial pressure exceeds the ventricular pressure, which means the AV valve is open, which means the ventricles are filling, but they're not being actively filled, right? They're actively filled by the atria. Well, that doesn't happen until over here. So back here, it's actually in the TP segment, same as here, right? After gotta go to the next, wrap this around, right? You have a T wave here. There's a TP segment, there's a P wave, right? During the TP segment, everybody's relaxed, right? No contractions, everything's relaxed. Venous flow is coming back to the atria, through the open AV valve, filling the ventricle up to about 70% or so. And so we're going to get our ventricular trace is going to do this. I'm going to have to put my label here. So after it closes. All right, so here's our ventricular volume going up and up and up. Right? Got my label over here for ventricular volume. So our volume goes up and up. Then the atria contract. Atria contract to pressurize the atrial blood, which squeezes it through the open AV valve. It's already open, and into the ventricle, which is going to boost ventricular volume even more. Right? Then I'm going to put little sort of demarcations here between our phases. Right? Then we have this phase where the AV valve is closed, but the semilunar is not open. In other words, the entrance door is closed, and so is the exit door. Right? Entrance is closed, exit is still closed as well, which means this phase is isovolumic. So I've got to have a flat line here, all the way over to about here. Right? I'll label all these in a second for you. Then we eject. So as we eject, of course, volume falls, right? That's the point of ejection, is to squeeze the ventricular volume out into the arteries, or at least, again, a portion of that volume. So we have our ejection phase. And again, I have to stop it over here when that semilunar closes. So we've got to go to about here. Right, drops very rapidly to right about there. And then the AV doesn't open immediately. We have to go between here and here. Right? So that's isovolumic. And then the AV valve opens, and we're back over to passive filling. This is where we started over here. So we can start this line coming up again. And active filling again. Right? And over again. Breaks here. Okay? So let's label them though. Right? So we've got passive filling. We've got active filling. Again, active filling of the ventricles by the atria. Right? Passive filling without atrial help. We've got the isovolumic contraction phase. Remember, you're going up in pressure here. Right? So it's a contraction phase. Then we open the valve, so this is ejection. Then we're down here, right? So the pressure is falling dramatically, right? So we're going this way, right? So our pressure is falling, so that makes this isovolumic relaxation, running out of room, okay? And then the AV valve opens, and we're back up to passive filling, active filling, abbreviations here, and we're good. Right, we've got all of our phases, right? So if you've got this, if you understand it, you actually understand the cardiac cycle in its completeness, right? The whole cycle. You understand when the valves are sort of opening and closing because you understand, you know, the cycle of filling and ejecting and all that kind of stuff, right? And again, correlating the mechanical things with the electrical things, right? Like students often are confused by that. I want to make sure you're not, right? The electrical things are the voltage changes of the cells or of the heart as a whole. The mechanical things are what happen in response to those voltage changes, right? The depolarizations and the resulting calcium influx and release inside the cell leads to the mechanical things, the changes in pressure that drive the changes in flow down here. All right, now the last thing to put on here would be, I'm trying to find a label. I'll use white, I guess. We'll use yellow. All right, so our maximum starting volume here before the ventricle starts to eject is the volume at the end of its diastolic phase. In other words, its systolic phase, right? And again, that would be, you know, all the way over to here, really, right? You'd be at maximum volume. It's not, remember, it's isovolumic here, so the volume's not going up, right? So during that flat line phase there, we're at our end diastolic volume. Then we eject a certain volume, which we'll see in the label in a second, and we end up at a minimum volume. Remember, it's not zero. The ventricles do not eject all of the volume that they contain. They do not eject all of their EDV, and you end up with your end systolic volume, right? The volume at the end of systole, at the end of ejection, right? The difference between the two, so EDV minus ESV equals stroke volume, right? So the difference between here, right, and here is stroke volume, top to bottom, right? Peak volume to minimum volume, stroke volume. Now, we often assess cardiac performance by looking at, well, what is the percent of EDV that you're actually squeezing out, stroke volume? Are you squeezing out a very high percent or a very low percent or a normal percent, right? It's a way of assessing how well the heart is contracting. And so the way to figure that out is just put it as a percent. And so what we do is the ejection fraction, EF, sorry, I don't have a lot of room to write things out here, but our ejection fraction, EF, is going to equal stroke volume as a fraction of EDV. In other words, how much did you eject, stroke volume, as a fraction of the total, of the amount that you started with, right? And so, you know, if it was 200 mils of EDV and stroke volume is 100 milliliters, well, guess what? Your ejection fraction is 50%, which is actually a little bit low. But just to give you an example, usually normal ejection fractions are between about 55 and 65% in normal people. It can go higher during exercise, and it can go lower during disease, in disease states. Okay, I think we have everything on here. Remember, we will talk about changes to cardiac performance, right? And there are two ways to do that, either through heart rate and or through stroke volume. Usually you're doing both at the same time. If we change heart rate, all we're doing is getting our nodal cells, remember we didn't draw them here, but if our nodal cells fire faster, all of these other events occur more times per second, right? If this is at rest, this whole cycle is about 1 time per second. You start to exercise moderately, it can go up to 2 times per second. We have to squeeze 2 of these complete cycles into the same time frame. Crazy fast, hard exercise, you can get it up to 3 times per second, a heart rate of 180 beats per minute. Some people even get even higher than that, especially young people. When we start talking about altering stroke volume, right, altering heart rate would squeeze things together. Altering stroke volume, we have to be changing this trace, don't we, right, because this is ventricular volume. So in class we talked about things that increase EDV and also things that tend to decrease, typically ESV. In other words, generate a harder contraction to leave less blood behind, right? And so if we make the top go up and we make the bottom go down, the difference, stroke volume, goes up. If stroke volume goes up, cardiac output goes up.